How do we perceive it?
How is it measured?
And most of all,
How does this tube work? In this video, we'll explain a few of the concepts involved in the workings of this device, the Rubens tube.
Let's start off with sound.
Sound is a mechanical wave which is created by vibrations of an object, causing the air around it to vibrate. The human eardrum picks up this vibration and vibrates as well, which translates to the brain as sound.
Three factors that determine how we perceive sound are frequency, wavelength, and the speed of the wave. Frequency is the measure of cycles per unit of time, and the wavelength is the length of one cycle. A relationship between the three is speed equals wavelength times frequency. So if two sound waves have the same speed, the one with the greater frequency has the shorter wavelength.
Most of us can hear sound, but can we see it? Well, we can't exactly see sound, but we can use it to create what's known as a standing wave. Here's how we did it.
The tube is filled with gas and lit on fire, causing flames to shoot up from the holes. The wave changes as different frequencies are played.
How do sound waves interact with the tube?
The sound from the stereo bounces off the end of the pipe, causing the two waves, the one from the stereo and the one from the back of the pipe, to meet, changing the pressure throughout the tube.
To begin explaining what's going on in the tube, we should start with flow rate. The flow of gas out of the holes can be modeled by Bernoulli's equation. The velocity should be proportional to the square root of the difference between the pressure in the tube and the atmospheric pressure. As the waves rebound off the end of the tube and return to the speaker, the pressure at different locations changes. This is known as wave interference. The air, water, or other medium that the two waves are traveling through takes on a shape as a result of the net effect of the two waves. At certain points, a high-pressure peak coming from the speaker will meet a low-pressure trough reflecting from the end, and the pressures will cancel out, which is known as destructive interference. At other places, two high-pressure peaks will combine, or two low-pressure troughs will combine, known as constructive interference. The pressure in the tube is the result of the sum of the waves that come from the speaker and reflect off the end, which causes a standing wave. Both constructive interference and destructive interference cause the wave shape that you see here.
Let's wrap this up with some music.